So I start the last part of the morning, and I called that part optical measurements. And this is a file with 63 slides. So it will take us probably 1 hour and a half, something like this. So again, I'm back on my strategy for the measurement of appearance, and we are now in this part here, which is we have the samples, and we try to make optical measurements to characterize the appearance of those samples. And as I said before, we have a very good story about it. We have developed the photometry, the colorimetry, the XYZ space, the C-lab space, and all the metrology. And it was, we were really happy with this. Thanks to this metrology, we could help industry to control the color of its production, control the gloss of the painting of the cars. We could even control the full calibration chain on about the scanner of the picture and then the display on a calibrated display of the color, and then I can print it on a printer and I get the same color. All those things have been developed and it works. And then came the 91 century and people developed surfaces like this, where you have effects that are called goniochromatism, or also like this, where during many years in the automotive industry, people were doing very high glossy paintings, and now they start to do it satin, and even sometimes matte. Or the same for the dishes. You have people who are doing things very glossy, so we developed the metrology to control that glossiness, and now they do stuff completely matte. Also this, that we call the sparkle. This is very small flakes, it's a very high reflectance, and it gives very bright spots in a very narrow direction. Or people ask us to characterize this surface, which is anisotropic, so you have to make the measurements for all the azimuths. And also this. So this is skin, it's translucent. And we want to match the appearance of the skin with prothèses of noise that are made with a 3D printer. And all those things, we don't measure it. In fact, we don't control it. And last but not least, there is also this, which is not really a question of appearance, but it's a question of security for builds or of functionality for hydrophobic surfaces. Those surfaces, they have properties that are made to get a functionality, and it's also optical, the way we should find to characterize them and control them. So we have to find, for all those applications, a way to develop a metrology. And what we can see is all those effects, they are strongly directional. And in fact, they are even strongly bidirectional. They depend upon the direction of illumination and the direction of observation. So we need to develop a new radiometric quantities to answer this industrial needs of characterization of the surface that they are producing now. And it means that it's still reflectance and transmittance measurement, but it's bidirectional. Bidirectional reflectance distribution function, transmittance distribution function, and even bidirectional surface scattering when we talk about the translucency. The quantity, it's still the reflectance. So the reflectance is the ratio of the radiance in one given direction by the irradiance from a given direction, which is different than the classical quantity, because the irradiance usually is defined only as the flux that is coming on the surface, whatever the direction is. In those quantities, we have also to specify the direction where the flux comes from for the illumination. And the unit is the inverse steradian. If you look at the reflectance, you have, according to the angles, you have the BRDF. If you look at the transmittance, you have the BTDF. If you look at the light that is crossing the interface, interacting with the structure, and is re-emitted not in a random direction, but in a given direction from the subsurface, we call this the BSS RDF. It's even more complex here because you have to look at the radiance at a place, at a position that is different position of the illumination. But it's life, we have to do this. So we do this with what we call a goniospectrophotometer. And because you are here, I would like to explain you why it's a goniospectrophotometer and not a goniometer, a goniophotometer, a goniospectroradiometer, a gonioreflectometer, all those things that I can hear everywhere as soon as we start to talk about BRDF measurement. In fact, there is a reason. The goniometer, something we use to make measurement of the refractive index. The goniophotometer, it's a device that is doing the measurement of the luminous flux by integration of the luminous intensity on the full hemisphere. A gonioreflectometer, it might work only for measurements that are done in reflectance. And it's a pity because most of the goniospectrophotometer are here because they can do reflectance or transmittance measurement in the same way, whatever because of the construction. A gonioradiometer, I don't know what it is, but a radiometer is a device that is measuring flux in watts. So I don't see why we should talk about this because we do, usually we do spectral measurements. And also a goniospectroradiometer. So a spectroradiometer is a device that is doing radiance measurements. Where a spectrophotometer is a device, this is the name of a device used to do reflectance and transmittance measurement. So if we talk about doing reflectance and transmittance measurement directional, then it gives logically the name goniospectrophotometer. So we had this discussion in the technical committee at CIE and we took this decision. I know that there is a confusion because usually the radical photo is for photometry, so V lambda integrated. It's not my fault if we call a spectrophotometer a device that is performing spectral reflectance and transmittance measurement. It's there, so let's use it. And try to use it on your side also, particularly when you do publications, because now the community start to know it and you will get a bad review. What is sure is if we are able to make BRDF, BTDF, BSS RDF measurements, we will have information that is related to all those visual attributes. Because this is my surface, I illuminate the surface from this direction, that I can control with my device. And for instance, the light that will be re-emitted in the specular direction, it will somehow be linked to the sensation of gloss. The light that is crossing the interface, interacting with the pigment, maybe changing its spectrum according to the direction of observation, right? Why not? But this very diffuse light will be linked to the color. The light that is crossing the surface, its transparency. The light that is re-emitted after a travel in the surface in the hemisphere, it's the translucency. Those small dots that we can get here in different directions, it's probably linked to the sparkle. And if I rotate my sample on an azimuthal angle, and if I find different values, that's because the sample is anisotropic. So from all those measurements, I should find in this very complex function information that is linked to the visual, the different visual attributes that I need to characterize the full appearance. Even if I didn't mention it, but we have in Europe equipments that are doing bidirectional fluorescent measurements. So they are, for each direction, you can illuminate the sample at a given wavelength and then measure the radiance at other wavelengths to see the fluorescence. So all is possible as long as you have time and as long as you have the proper device. Very quickly, because we will come back on this later, but this is, for instance, a BRDF measurement of a spectral from LabSphere, which is used for the calibration of spectroradiometer. And usually people make the assumption that this sample is Lambertian, so has the same reflectance, whatever is the direction of observation. If you take a device and if you illuminate the sample, not from the normal direction, but at 60 degrees, you see that BRDF, for instance, is not a sphere. So if you make the assumption that your sample is a perfect diffuser and you're looking in this direction, you make an error of 300%. Good to know. You can do the same thing for goniochromatism. You can measure according to the direction. So I will show you now a lot of results like this. Here you have the azimuthal angle. If you have here it's the direction. I'm not sure, in fact. Is it the angle? Because now I see A and B, and maybe this is the value. So according to the directions. Well, in fact, we can plot in the AB diagram, according to the direction of illumination, the color of the surface that is changing. So it's not what I wanted to say. It's more this one, where here you have the zenithal angle in abscissa. The zenith, if sample is like this, the zenith, it's the angle from the normal, and the azimuthal angle, this is this angle when you rotate the sample. So here it's usually we plot the BRDF as the reflectance seen from a space, where in abscissa you have the zenithal angle, and in ordinate you have the azimuthal angle. This is for gloss, so we see the specular in the direction of the specular direction is here, and you have the specular peak here. One last thing, for instance, that is funny, it's that kind of measurement where you have here an hyperhydrophobic surface that is made of micropillars that have a size of 30 microns. And so, in fact, with the light, it gives the grating. And you can see in the BRDF, you can see the different diffraction peaks that are linked to the structures. If you have the angular, the good angular resolution, because the grating has a step of 30 microns, so it gives different orders every 0.4 degrees. So you need a very good angular resolution. But today we can do that kind of measurement. We can also measure sparkle. The dots here, you can see them on the BRDF. This is the small peaks here. And it's just to show you different value, but we will come back on this later during the afternoon, more in details. So I hope you are convinced that it is very useful to do those measurements, and because now you can find optical parameters that will be useful to characterize or to be used to correlate with the results of psychophysical experiments that will deliver the visual signal of sparkle of translucency. And because you are very motivated, you want tomorrow to start to build your gonio, and I'm here to try to give you advices. So what I'm going to talk about now, it's about a practical approach for BRDF measurements, how works a gonio spectrophotometer, what matters in this device, how to adapt the gonio to the sample under test, and talk a little bit about the uncertainty and the classical errors that you might find in this device. Hope you're ready. Let's go. We start with the measurement equation because, again, we talk about the measurand. So the measurand is reflectance. The reflectance is the ratio of the radiance by the irradiance in a given direction. So if I put here the things, clearly this is my sample. This is the normal of the sample. I will define the direction of illumination by theta I, the zenithal angle, and phi I, the azimuthal angle, and theta O and phi O for the direction of observation. And now we are not talking about something that is, you're not going to do radiance and irradiance measurement with a radiance meter and radiometer. You will develop your quantities. So the radiance, it is the flux inside a given geometrical extent, and the irradiance, it is the flux on a given surface. And all those things are, all those parameters at the moment, they are infinitesimal. So this is very small quantities, at least quantities that are not changing inside the given space. And you see with this equation, so my geometrical extent for the radiance here is given by the aperture here that I call S0, or the solid angle here that is defined, that is pointing here at the middle of the surface and defined by this surface here on the sphere. And on the other part, there is the illuminated surface here, projected in the direction of propagation. So this is the definition of the geometrical extent here, and here the surface. And you see that the surface, in the reflectance, the surface illuminated cancels. So at the end, what you have to do to make a BRDF measurement, it's to measure the flux in watts reflected in a given direction, O, direction of observation, divided by the flux illuminated the surface. Sign here for the that comes from the geometrical extent expression, and you also have to put the solid angle, which is this solid angle here, is part of the equation. This measurement equation is only valid when fluxes are homogeneous on the surface. This is very important because you see I moved here from the infinitesimal quantities to the real quantities, because we need to open to make a flux, otherwise we get nothing. And I am allowed to do this without making the integral of the angles, only if I can assume that the flux is homogeneous within this small surface here. Then I don't have to make the integration with the angle. And this is something very important because sometimes, for instance, when you talk about measuring the light in the specular direction, it varies very quickly with the angle. So you can't really say that it's homogeneous if your angle is too high. And then you measure something completely. So be careful, keep this in mind. Same here on the surface of illumination. I will say it, I think, several times because it's important. It's not important, but it's something people forget sometimes, and then they don't understand. At the end, so yes, we need to do a flux ratio. We need to control our solid angle, and we need to be able to generate all the direction of illumination and of observation. And the direction of illumination, it's zenithal angle, azimuthal angle. Observation, another zenithal angle, azimuthal angle. So it's 4 angles, 4 degrees of freedom. So we will need 4 rotation, a capacity to measure flux. We need to control the wavelength because it's a geometric quantity. We need to control the polarization. And we need to control the solid angles because it appears here in the equation. And now we can start to really talk about what you will put in your gonio spectrophotometer. So first you need to take care of the mechanics to be able to make your rotations clean. You need to think about, are you interested only in the reflectance and but also in the transmittance at the beginning? Because for the transmittance, you have to go the other hemisphere. So for instance, if your sample is taken like this, fine, because you have your sample holder and you're dead. So you have to think about it at the beginning. We'll talk about it. Then the sample also, you have to really think, what are you trying to measure? It will not be, you will see that it's not at all the same design if you want to characterize the gloss, the goniochromatism, the sparkle. So, and you won't get the gonios that can do everything, unfortunately. So it is very important for you at the beginning to ask yourself what we will do with this device, because it will drive the full optical design of the detection. Also, what type of illuminated surface? Typically, if you want to characterize the textile, like my pant, the appearance seen from this distance, usually you will get, you need to have the average, so you need something like that is larger than the texture of the textile. So let's say that the texture is about 1 millimeter. It's something larger, let's say 10 millimeters. But if you get 10 millimeters, when you will illuminate your sample with an angle of 80 degrees, for instance, then it's 10 millimeters divided by cosine 80 degrees. It gives about 50 centimeters, the projection. You need to rotate around this. So around 50, then it gives 1 meter of diameter. And you need a little space behind to make to put your detection, and then you arrive with something that is 2 meters of diameter. And it's just because at the beginning it was 10 millimeters. So think about it, because maybe you need a room where instead at the beginning you had just a desk, and so this is part of the reflection you need to have before. Think also about the liquid, the creams. Because the liquid, you can't put this like this and rotate. You need to be, of course, horizontal. So it's not the same design. Operational constraints. What about the measurement time? If you are in a meteorological institute, we don't care about time. You can spend 1 full week if it's needed. But if you are an industrial, you need to do 1 measurement every minute, it will not be the same design. What is the illumination strategy? We'll talk about it later. And also for the optical parameters, what kind of wavelength are you looking for? Is it just visible or is it infrared? Visible, UV, it's not the same detection, it's not the same problems also in terms of stray light and everything. And what is the bandwidth? What is the spectral resolution you need? It's not the same for color and for gloss, for instance. All those questions you will have to ask yourself about that before you start to build your gonio. And I will go over all this quickly. First, the mechanical design. So this is 6 different gonios, for instance. They are all performing BRDF measurements, and they are all completely different. Not completely, but they are different. This one is one that is at PTB in Germany. It's you see the sample is at fixed. We don't see it. This is one at the Onera, which is made to characterize the BRDF of snow. Of course, the snow, you don't put it like this on a gonio because of the so it has to be horizontal. So then they had to build a full arch around the sample to be able to characterize this surface. This is another one at NIST, which is National Meteorological Institute of US. It's different than the one in Germany because there is no robot. It's a classical rotation. This one is similar to the one at PTB, but the robot is a different place. This is a full gonio, but completely optically based. I'll talk about it later also. And this is, for instance, another gonio at a university that is working mainly with the lasers, for instance, so the dimensions are different. About the mechanical design, your gonio is always made of 3 parts. You have the illumination, the sample holder, and you need always to get 7 degrees of freedom. You have the 4 angles, but you will need also to put your sample at the middle of the gonio. On a gonio spectrophotometer, you have 1 point in the space, which is the point that is at the middle here. This point is somewhere in the space, and your sample has to be put tangential to this point. And to do this, you need 3 degrees of freedom, 3 translation. 1, 2, 3, or something. Well, in the space, you have 3 dimensions. So it's 3 translation for the sample, 4 rotation for the detection, and 2 for the detection, 2 for the illumination. So on this gonio for soft samples, for liquid samples, you have 3 translation on the sample. You can put the sample at the middle of the gonio. It here to have exactly the surface you want to measure at the middle. And then you have 2 rotation on the arches here. They are different. Both of them can rotate. And you have also 2 rotation on the sample. One like this and one like this. This is another approach because this is for classical samples like paintings or whatever. So then you can put your sample vertical. It makes your life easier. You can use a robot, for instance. The robot will have 3 rotations, one like this, one like this, and one like this. And then you have a ring that gives you the 4th rotation. And the robot provides you also, if it's a 6-axis robot, you have a 3 rotation and 3 translation to put your sample at the middle. So it's quite convenient. Now I'm talking about the robot. In fact, we have seen a lot of robots in the last decade into gonio spectrophotometers, but in fact, you can also use a more classical device. Here you have the 3 rotation also. One is here, this one, and here you have also a rotation to rotate along the azimuthal angle, and it works also. It is put on translations stage to put the sample exactly at the middle. What is the pro and cons? The robot is cheap. Well, cheap, something like this, it's about 30,000 or something euros, but something like this, it's about 100,000. Because there is a lot of long distance rotations. So that's why I say cheap. In fact, it's not cheap. And it's very fast in the way you control the rotations because it's a robot. It's made to work in industry. On the other part, it's not accurate. Even if they tell you that it's accurate at 1 micrometer, in fact, it's not true. So it's less than this. And 1 micrometer, it can be significant, in fact. This is very accurate. That's why it's more expensive.